So this is problem 8 of the CSM mock final for CS61B. So what we're given this problem is a string of input prices. And of these purchase price, we wish to compute the median price at any given instance. We also want our algorithm to run in big O of log n time. So we want to fill out the purchase median class. So something to note before we get started is that if we have a even number of inputs, then we simply just take the average of the two median and then return that as our median. And then down here, just ignore this num. It's a little bit of a typo. We'll find out that we won't need this later on. All right, so let's go ahead and let's just draw this out real quick. Yeah. All right, cool. So suppose we have like this stream of data, 5, 1, 3, 2, and 1. And as this data is coming in, we want to compute the median. So I think the easiest way we can do this problem is that we can just insert all these elements in sorted order and we get the median of that array. So that works. However, we'll end up with a run of big O of n, which is not what we want. We want a linear time. So what's a better way we can approach this problem? Well, we can take all these items, and what if we actually drop them in buckets? So we can have a bucket on the left and then a bucket on the right. And what we want to do is that we want to add all the elements that are less than our current median into the right, and all the elements that are greater than our median at that current moment, we want to add it to the right bucket. And from these two buckets, we want to form some type of data structure that's really quick to be able to get the minimum or maximum value at a certain time, given the time frame that we want to run in big O of log n. So that's really hinting towards we should probably look at using a heap. So from these two hits, maybe on the left side, we can keep a max heap. And then on the right side, we can keep a min heap. So that way, if we wanted to access the median element, then all we have to do is that we can just simply compute the size between the min and the max heap. And if it's the case that one is bigger than the other, we just we just pop off the element. Sorry, we just peek at the element that is of the larger heap. So let's go ahead and just run through an example of that and see how it would kind of work. So our first element is 5. That's pretty trivial. It's just 5. So let's just go ahead and drop it inside of our max heap. And now 1. We notice that 1 is less than 5, which is our current median at the time. What we want to do is that in order to like maintain balance between the min heap and max heap, in other words, we want to keep them relative to the same size with a difference of 1. We're going to go ahead and just drop it inside of this max heap. And now we want to, and now that we have the max heap and the min heap differ by size of 2, we want to evict the 5 and then inside of the min heap. So now if we wanted to compute the median, then all we have to do is that we can just peek at the element here and the peak at here, since they're of the same size, and then compute the average. All right, so let's go ahead and move on. When we add in a 3, we notice that 3 is less than 3 is equal to 3. So it doesn't really matter which bucket we throw it into. Let's just say for consistency's sake that we just throw it into the max heap. Now we perform our check. Does our max heap exceed our min heap by more than one element? And no, it does not. So we go ahead and carry on. If we wanted to compute the median, all we have to do is that we can just check the size between the min heap and the max heap. We notice that the max heap has more elements. It has one more element, in fact. So simply just get the maximum of the max heap, which is just 3. So moving on to 2, we notice that 2 is less than 3. So what we want to do is that we want to add 2 into our max heap. And then now we figure out that, hey, our min heap and max heap differ more than one element. So we want to evict the top element in our max heap and put it in the min heap. So we evicted 3, and then we put it into this max heap. Now, if we wanted to compute the median, all we have to do is query the min heap. This will give us a 3, and then query the max heap, which will be a 2. And then the median between the two would be a 2.5. Right, I think we kind of get the general idea. So let's go ahead and just start coding this up. Let me go ahead and pull up my code editor real quick. Cool. All right, so earlier I just noticed that the text was too small, so let's go ahead and just I'm gonna go ahead and record this portion. So what we want to do is that we want to create 2 priority queues, one min heap and one max heap. So let's go ahead and do that. We want to create this max heap, and remember that in Java the default priority queue is a min heap. So we want to pass in the comparator that reverses the order of it, so that essentially just gives us a max heap. And then let's go ahead and initialize a min heap, and it'll be in just regular order, so we don't need to pass in the comparator. All right, cool. Now that we have that, let's go ahead and work on this add num method. So earlier we alluded to the fact that we want to be adding to the min heap or the max heap. So let's just go ahead and like skeletonize that real quick. So if for some condition we want to add to the max heap, so max heap dot add num. Oops, sorry, add num. Else we want to be adding to the min heap. So in the max heap condition, we remember that the max heap is the heap that sort of represents all the elements that are less than or equal to the median. So to be able to figure this out, what we should do is that we should take the number and then we'll compare it to the min heap, the min item of the min heap. So that peak. And then if our number is smaller than the minimum item in our min heap, then we want to add it to our max heap. Something to do, keep in mind is that if our min heap is empty, this might throw an error. So we probably want to check to see if the min heap is empty or not. So not min heap that is empty, and our number is less than the min heap. If that's the case, then we add to our max heap. And then earlier on that we mentioned that if adding to the min heap causes there to be a difference of sizes between the two heaps to be greater than 1, then we want to evict that item from the max heap and then put it into the min heap. So let's go ahead and do that. So if the max heap dot size is greater than the min heap dot size plus 1, then we want to evict the item from our min heap. I mean our max heap. So we'll do max heap dot pull. So this evicts the maximum item, and then we want to add this item into our min heap. So we're going to do min heap dot add. Cool. So that takes care of that case. And now, if our number is greater than or equal to our min heap, then we want to just add it to our min heap. So let's go ahead and do that. And then remember, in that case, we also want to check to see what the size of the min heap is. And then if it is the case that the min heap differs by the max heap, by the size of both of them differ by 1, then we want to evict that item from the min heap, then put it onto the max heap. So we say if min heap size is greater than a max heap size plus 1, then we want to evict the item. So min heap dot pull, and we want to add that to the max heap. Cool. So that's that for the add num method. Let's go ahead and move on to the find median method. So in this case, remember that we are curious in the size difference between min heap and max heap. If it is the case that min heap has one more element than max heap, then we know that the item exists within our min heap. Similarly, if there's one more item within the max heap than it is in the min heap, then we know that we want to look inside of our max heap. So if it is the, so let's go ahead and do that. If it is the case that min heap dot size is less than max heap dot size, then we want to pull the max heap. So we return max heap dot peek. Sorry, we want to peek at it because we don't want to pop off the element. Otherwise, if it's the other way around. So if min heap is greater than max heap, then we want to peek at the min heap. So we want to go ahead and just return min heap dot peek. And then finally, when both of them are of the same size, we'll just peek at both of them. So we can do the max heap dot peek plus min heap dot peek. And then from these two, we can just compute their average. And then obviously we want to return this at the very end. And that's that for that problem.